When you bend your knee, your quadriceps muscle is stretched. This increases the tension in the quadriceps tendon attached to your patella, which in turn increases the tension in the patellar tendon that attaches your patella to your tibia. Simultaneously, the end of your femur pushes outwards on the patella. What's the magnitude of the force that the femur exerts on the patella if the tendons are oriented as in the figure and the tension in each is 60 newtons? All right, so let's start by drawing our free body diagram. And we'll represent our patella as this dot, and we'll put it on an XY axis, and we'll mark here positive X, positive Y, and now we'll draw in these forces we have. So we can see that the force of the quadriceps tendon, which we'll call FQT, is oriented like so. And then we'll put in the force of the patellar tendon, FPT, oriented like so. And that's 42 degrees below the horizontal. And then now the force that we want to know something about, which is our F femur. And that's going to be going off something like this, but we don't really know exactly what's going on with it. So that's what we want to figure out. And maybe we're not sure initially how we're going to find that, but if we think about what's going on in our knee when we bend our knee, maybe crouch down a little bit, we know that the patella is not accelerating. So if the patella is not accelerating, we can look at Newton's law, and we can see that if A is 0, then F net is 0. So if we know that F net is 0, that means that F net in the x direction is equal to 0, and F net in the y direction is equal to 0. So maybe we can set up some mathematical expressions for F net x and F net y that might help us solve for the x and y components of our femur force. So first we can do F net x, and that will be equal to the sum of all the forces in the x direction. So FPTx, FQTx, and F femur x. So immediately we can look at FQT and see that it's oriented directly along the y-axis, so it will have no x component, and that can go to 0. And since we know that F net x is also 0, we can rearrange this and find that F femur x is equal to negative FPTx. So we look at FPT and we see it's kind of shooting off this way, and we really don't know what exactly it's doing in the x direction. So let's break it up into vectors. And this blue dashed line will be the x component of the patellar tendon force. So that'll be FPTx. And we can also check out the y component of the patellar tendon force. So that'll be FPTy, which we're not working with yet, but we might use it later. So if we want to find out the magnitude of this, we can use our trig functions, and we can say that FPTx equals FPT cosine 42. And now, how did I get that? So if we look at our cosine function, cosine 42 will equal adjacent, which we can see the adjacent is FPTx, over hypotenuse. And we can see the hypotenuse is actually just FPT. So if we just rearrange that, we can get FPTx equals FPT cosine 42. So now we can see that if we plug in what we got for FPTX into here, we can see that F femur x equals negative 60, which is FPT, given in the problem, 60 newtons times cosine 42. And I believe we're going to get, let me just punch this in the calculator, 60 times cosine 42, and we get about 44, it'd be negative 44.6 newtons in the x direction. All right, so now let's work on F net y. So we know that F net y is equal to the sum of the forces in the y direction. We know it's equal to 0 as well. So let's see, FQTY plus F femur y plus FPTY. All right. So we know that FQTY is just going to be equal to FQT because it's oriented directly along the y-axis. So we can just go ahead and write in that that'll be positive 60. But F femur y, we don't know. And FPTY, perhaps we could figure that out with trig similar to the way that we figured out FPTX. But now we're going to probably use a different trig function. So we can maybe say sine 42 is equal to the opposite, which would be FPTY, over the hypotenuse, which would be FPT. So if we rearrange that, we can say that FPTY will equal FPT sine 42. And it'll be negative because it's in the negative y direction. So we can rearrange this and find that F femur y equals 60 newtons minus, this will be negative F femur y, minus FPT sine 42. All right, so let's see. 60 times sine 42, we get 40.1. So now 60 minus 40.1, so that's FQTY minus FPTY, 60 minus 40.1, we get 19.85, and so F femur y equals negative 19.85 newtons. Okay, so now it looks like we have F femur x, and we have, let me find a color, F femur y, but we still don't know what F femur is. So if we redraw this triangle down here, so F femur x, F femur y, and we know these magnitudes, so we can fill that in. So this is negative 44.6, and this is negative 19.85 newtons and newtons. And so now we want we can use our vector addition and we can find this, which is F femur. So we can use the Pythagorean theorem, and we'll see that F femur is equal to the square root of F femur x squared plus F femur y squared. So let's punch that in. 44.6 squared plus 19.85 squared square root, and we get about 49 newtons. So we know the magnitude of the femur force now, but we want to know one more thing, and that is what is the direction of the femur force. Well, we know it's going to the left, but what is this angle theta here? So we can do one last trig function to find out this angle. So we know that tan of theta is going to be the opposite over adjacent, but if we use tan -1 of the opposite over adjacent, we can find theta. So we know F femur y and F femur x. We have these numbers, so we can go ahead and do tan -1 of F femur y over F femur x. So that would be tan -1 of 19.85 over 44.6. And let's punch that in. And we get about 24 degrees. So this angle theta equals 24 degrees. So we can say all in all that the femur force is 49 newtons to the left, 24 degrees below the horizontal.